fx we can put as x. Fx you can put as x. If you put as x, then you can solve this. What is the solution for this problem? That you can easily find out. Easy problem. So that means final solution will be this will be eigenfunction solution. This will be simple solution. If you add it up, that's it. You got the answer. If you add it up, you got the answer. Next problem. The question is find the eigenvalue and eigenfunction for the operator. Find the eigenvalues and eigenfunction for the operator. Question is find eigenvalues, eigenfunctions for the operator. Operator is dx of x du dx plus 2 by x u. And the boundary condition of course 0. Without that we cannot have the eigenvalue problem. So what will be your operator then? This is by default the Sturm Liouville operator, ddx of dx du dx plus qx u equals to minus lambda wx u, right? So finally what you get? Your eigenfunction equation. What's the eigenfunction equation? What is your eigenfunction equation? What's the eigenfunction equation or eigenequation? What's the eigenfunction in Jessica? Expand and give me the answer. Px equals to x, right? Yeah. Ux equals to 2 by x. What's the eigenfunction equation then? Lu equals to what? Equals to Lu equals to what? Lu equals to minus lambda, that's all. This is the situation, I don't know. At 3-4 times I have to shout for the answer. This is the way to teach mathematics, I don't know. What is the eigenfunction right hand side? Eigenfunction equation. ddx of x dun dx plus 2 by x un equals to what? Lambda w then un. It takes so much of time for you to. My God, 3-4 times I have to talk. I have to shout. Okay. Then if you expand it, what will actually happen? If you expand, what will you get for answer final? If you expand, what you are getting? X square? X square what? X square what? You are just saying x square. Then we are not to talk, okay? What x square? Is it x square only? d2 by dx square. See, this is the kind of thing I don't like. If you don't want to talk, don't talk. Yes, next, Vasudha. Plus du or x cube dx. See the kind of situation. X du and dx. Then plus 2 by x un equals to minus lambda w un. And then what you can write? This 2 un, right? This should not be 2 by x, 2 un. X square I am saying, 2 un. So it is combined, you can write lambda w plus 2 un equals, what is w by the way? What is wx? What is wx? Can you find wx? Okay, so Wx could be 1 by x. If Wx equals to 1 by x, what actually happens? Should be, I think x will be there, right? 1x will be there. Check it out. Okay. Lambda Wx into x. If Wx equals to 1 by x, what actually happens? It is lambda plus 2, right? Wx is 1 by x into x is lambda plus 2, right? Yes or no? You didn't get it? What I am doing? What you didn't get? Simple as I kept you didn't get, huh? My God. I don't know why I am teaching all those things. I am just saying I am assuming Wx. So Wx can you find out? Of course you cannot find. There is no reference problem. So you can take any Wx. Yeah. Provided your orthogonality has to be maintained. Okay? See, point is, if you put Wx equals to 1, you cannot do anything for this problem. Why I am putting Wx equals to 1 by x? See, whatever Wx you will be taking, whatever eigenfunction you have, that eigenfunction is orthogonal with that respect to Wx. Okay? We will show why this Wx I am putting 1 by x. I will come soon. What kind of problem this is? If you put Wx equals to 1 by x, it is x squared dq un by dx squared plus x du un dx plus lambda plus 2 un equals to 0. This is a Cauchy-Euler type problem. That is a Cauchy-Euler type problem. That's why I am putting Wx equals to 1 by x. And what's the substitution? X equals to e to the power t, right? Substitution is x equals to e to the power t for equidimensionality. Substitution is e to the power t for equidimensionality. X equals to e to the power t, Cauchy-Euler type. Cauchy-Euler type. What's your solution then? What's your solution then? What is u and x? Cauchy-Euler type. What is the general solution you got? What's the characteristic equation? Characteristic equation? What is that? Correct. Correct. What's the eigenfunction then? General form? What is that? Yes, what is that? C1 cos into T. T you have to replace by x, no? Very good. Okay, you are getting rightly. U and x is nothing but, we can say an cos root lambda plus 2 ln mod of x plus bn sin root lambda plus 2 ln mod x. Now apply the boundary condition and get me the proper eigenfunction, eigenvalue. I want eigenvalue. It should be lambda n. When you put un, it should be lambda n. You can put lambda n here. It's better. Typical eigenvalue problem, lambda n. What is lambda n and what is un? What is lambda and what is un? What is lambda and what is un? Lambda is how much? Give me n square pi square by es minus 2 or plus 2. Always we are having some problem with minus or plus. Minus or plus? Plus. Plus, yes. So lambda n is 2 plus n pi ln 2 whole square. Now we'll decide whether n equals to 0 or not. One predicate is there, 0 is there, question mark. What is unix? an cos what is that in bracket? n cos what? Root over lambda plus 2 is how much? The board, everything is there. I am not getting any answer. Root over lambda plus 2 is how much? Root over lambda plus 2 is how much? 4 plus. How can you say 4 plus? Root over ln plus lambda 2 is how much? Is the lambda you got satisfied? Is plus 2 or minus 2? Minus 2, okay. Things like mistake I have. Check it out, minus 2. Okay, then what is the a values? What is that? n pi by ln 2 ln x. Now decide whether n equal to 0 is acceptable. Now decide n equal to 0 is acceptable. If n equals to 0, what actually happens? Since a cos function, cos of 0 equals to 1. So n equals to 0 is acceptable eigenvalue because it gives non-zero eigenfunction. So this is one of the classic examples where n equals to 0 is acceptable for eigenvalue because it is giving the non-zero eigenfunction. Okay, last part of this is solvability criteria before I go to the differential equation, PDEs. Before I go to the PDEs, last is Fedorov alternative theorem. Fedorov alternative theorem, what we actually learned earlier, n equals to f and bu equals to 0. Right? This is a boundary operator. What's the adjoint problem if you are constructing? L star b equals to 0 and b star b equals to 0. This is the adjoint problem, right? And what's the condition from the pedagogic theorem for sublimity? Do you remember? We have done from the vectors. In the vector space it was Ax equals to b. Adjoint problem was A star b equals to 0. There was no boundary condition. What is the sublimity criteria for that? It is there in your class note. It is there in the class note. I don't know why you guys are coming to the class. I don't know. And why I am teaching you guys. Ax equals to b equal and A star b equals to 0. What is the sublimity criteria for Ax equals to b? We have done in the class. Inner product is Jessica. What is the sublimity criteria here? What is the sublimity criteria here? All the time you are comparing the vector space with functional space. All the time you are comparing vector space and functional space. What is the sublimity criteria here? Integral or inner product? We have done inner product there. Why you are talking in terms of integral? We have done it. You just now told me condition for sublimity for the vector space inner product b equals to 0. Right? What is the sublimity criteria here? In terms of inner product. What sublimity criteria? So many people are actually doing like this. Nobody is giving answer. If you cannot give, please keep quiet. Or raise the hand and give me the answer. I don't like this kind of coward attitude. If you want to give the answer, raise the hand and give. You could be wrong, no problem. Vasudha? So simple. Inner product F equals to 0. And this kind of thing people have no guts to tell also. How to prove it? Can you tell me the proof based on your vector space? You have the vector space proof with you ready? Your notes are there. See, you don't have not even opening the notes. You're so lazy. I don't know. You're so lazy. You're not even opening the notes. It is there the notes. Inner product LU equals to UL star B equals to 0. Because I am putting the boundary conditions such that binomial concomitant has to be 0. No question. Binomial concomitant has to be 0. L could be equal to L star, L could be not equal to L star, we don't know. But binomial concomitant is 0 so that we can actually satisfy this one. If this is non-zero, then you cannot do that. There is a problem. Then there is a problem. And since everything is 0, no problem. Next, this is not the criteria. Does anybody consider that? What's the next step? You said 8b equals to 0. How to get the next step, boss? L equals to F. With the next step, also I have to shout like this. Luckily, I have the mic. Otherwise, I have a big problem because of you guys. I don't know what class. Again, I am saying what class I have been. Last batch, I didn't have this type of problem. 1,000 people used to respond. I don't know what happened this batch. That's it. This is the criteria for the sublimity. Okay, so this is the way pedagogical theorem can be proved. In your assignment, one problem is that. Do you have the assignment 7 with you? Assignment 7, we have done so many problems, right? Assignment, if you look at assignment 1 we have done, assignment 2, problem number 2 we have done, problem number 3, orthogonality of eigenfunctions we have done, problem number 4, all the eigenfunction solution I think we have done, all the set. Okay? Problem number 5, 5A and 5B. See, it is given that approximation of function with a finite series of orthogonal function phi x using the weighted inner product, obtain the expression for the coefficient in the expansion. Then that is many times we have done, is very easy. Problem number B. Next, obtain the coefficients by minimizing the mean standard error. What do you conclude from your results in part A and B? In part A and B. What can you conclude in the problem part A and B? So please try to do that. What actually you can do that from here, if you write fx minus summation I equals to 1 to n ci fix squared dx, minimizing mean standard error. You remember least square error? Have you done least square error? LSE? You have done, I think you know in your school level, least square approximation, least square error. This is your data. Curve is going. This is error is negative, error is positive. Okay? Error is positive, error is negative. Sum of the square of errors, how to write? We have yi minus a minus bxi. This is yi. This is the value is xi. This is the linear equation y equals to a plus bx. So if you get the data directly from the line, which is a plus bxi, error is yi minus a minus bxi, correct? So the error square is, and sum of the error is this. How to get a and how to get a and b? You take dou e by dou a and dou e by dou b equal to 0. You get the two equations and solve it. You get the answer. Same way you can get it. Okay. So please look into least square error to get the answer. I cannot give all the things. Some of the things you have to really do yourself. If you cannot do by yourself, you will learn it, because I have seen that I am just doing spoon feeding, but nothing is actually working. So please do by least square. Any of the books, any of the things, you can get least square error. So you calculate the error and you have to find out dou e by dou a equal to 0 and dou e by dou b equals to 0. Same way here also. Here you have to do by dou e by dou ci equals to 0. Okay? Here you have to do dou e by dou ci equals to 0. For example, what I am trying to say here. I am plotting a curve, not a straight line. And this curve equation is y equals to a0 plus a1x plus a2x square plus a8x to the power n. The data is x sine y. What is the error? This is my error, right? EI. How to write the error? Error is yi is here minus, of course the error is here negative because we are with respect to this one, and this will be what? a0 plus a1 xi, a2 xi square, an xi to the power n. This will be therefore n data set 1 to m. This is called total error. How to find out a0, a1, a2, a? Dou e by dou a0 equals to 0. Dou e by dou a1 equals to 0. You will get set of linear equations. Okay? If you solve it, you get a0, a1, a2, a. Similar kind of problem. This is called as multivariable regression analysis or the least square analysis. So this, if you can look into, you can actually get it. So this kind of problem is already done in Grewal's book. You can look at Grewal's book and get an answer. Next, so with this we have done the basics in functional space. Functional space, what we have done? We have compared the vector space with functional space. We have looked into the linear operator, nonlinear operator. We have solved extensively nonlinear operator or nonlinear differential equations. We have done the eigenfunction analysis, eigenfunction solution. Before that, we have done the adjoint theorem. In the adjoint theorem, we have proved the different rules for the eigenvalues and eigenfunctions. And finally, we solved the suburbility criteria. and it solved lot of problems. So this much was done even your vector space, but vector space was very easy because there is no such called ordinary differential equation and partial differential equation. Right? In functional space, we have got so many things. So we have done ordinary differential equation. Soon we are going to start partial differential operator. Partial differential operator or equation. Between partial differential operator or partial differential equation. So partial differential equation of 3 types. Parabolic, elliptic, hyperbolic. Parabolic, elliptic, hyperbolic. In chemical engineering, so I will not tell you, I will not give you in a big problem as a class and say that okay, identify parabolic, elliptic, hyperbolic. As a chemical engineer, you should be able to find out. In fact, in the kitchen, every day we can see these two. And this equation occurs in atmosphere. So chemical engineers will be seeing all these equations every day. Not even chemical engineers, household work. So what actually happens, I am putting a water and Bunsen burner is there. Okay? And each point, temperature is different. So temperature is function of position. Right? Each point, temperature is changing. And since Bunsen burner is there, temperature is changing with time. Okay? So this type of problem, when temperature is changing with time and the position. Okay? And what actually happens that this portion is very hot. This portion is very cold. Not very cold, colder zone. Why? There is a resistance. There is a resistance between this. If there is no resistance, then everywhere you can get same temperature. How to get everywhere same temperature? Stirring. Yes, that's it. All chemical engineering things, all stirring. So if you put a stir, what actually happens? You remove the resistance. What is resistance term? Resistance term is K d2t by dx square in x direction. Resistance will occur in y direction also. Resistance will occur in z direction also. Okay? All three together we call K grad square T. And since we have all directions, we cannot write D, it will be rho. So we are introducing partial differential operator with rho because T is function of x, y, z and t. If T is the only function of x, you can write dt dx. Since the function of many variables, we have to write rho. So you have the equations like rho t by rho t, rho t by rho x, these are the kind of operators, and rho t by rho z. Okay? Yeah. So these are the resistance terms. So what actually happens if this type of system, if you want to talk about, is a heat transfer problem. In the heat transfer, what actually happens in a system, in the school level, we have seen QMCP delta. Right? QMCP delta T. M is mass, Cp is specific heat, delta T is change in temperature. Sometimes what actually happens, we talk about rate. So what actually happens, it is coming mCp dt by dt, which is dq by dt. This is the heat supply. This is the heat supply. This equation is actually assuming that There is no system resistance. Everywhere same temperature. Okay, everywhere same temperature. The system resistance is there. There is point to point temperature will change. Okay. So in that case, what actually happens? For example, you have a wooden block, hot wall, cold wall, and this is the temperature profile. So in this type of things there with the X, there is a resistance. If there is no resistance, temperature is like that. If there is a very high resistance, it will be very steep. So based on thermal conductivity, people can conclude if thermal conductivity is tending to 0, you will get this kind of profile. If thermal conductivity is tending to infinity, this kind of profile. This is a gate portion. It becomes gate portion. I am just giving you the gate portion. I told you, right? I promised. So that many of you should leave this place because this is a stop gap. Okay. So what actually happens? This is a heat sum, right? And now, if the resistance, this equation will be converted to mCp dou T by dou T, because thermal gradient means T has to be a function of x, one dimensional, which will be K dou 2T by dou x square. I am writing in terms of per unit mass. I am talking in terms of per unit mass. So, I am assuming that there is no Bunsen burner. I am switching off the Bunsen burner. I am just saying initially it is hot, this is cold, and each point temperature function of position and temperature, and from this it is coming like this, pure conduction. If there is a convection, what actually happens? Rho Cp dou T by dou T, it will be for the x component of velocity. So convection, due to convection, how the temperature is being distributed? By the thermal conductivity, which is called conductive heat transfer, and this fluid particle is moving. Why? Because here temperature is very high. Density of fluid is much less. Buoyancy. So the density of the fluid is, because we know the density is decreasing with temperature. If temperature increases, density decreases. So this fluid particle will become lighter compared to this. This fellow will be going here and this fellow is coming here. With that also temperature also will change point to point. So one temperature is changing by this conduction mechanism, okay, which is already taken care. Another is by the convection mechanism. And convection means we have the Vx, Vy and Vz, three components. Right? Okay. So what actually happens? This is called advection term or convection term. So because of that, what will be the amount of heat transfer? What will be the amount of heat transfer? If a fluid particle moves with velocity, say v, how much heat will it will carry? How much heat will carry? How much heat it will carry? That's also transfer will be there. So that will be taken as Vx dou T dou x, Vy dou T dou y, plus Vz dou T dou z equals to K dou 2T dou x square plus dou 2T dou y square plus dou 2T dou z square. Correct? So this is your sensible heat. This is for the fluid particle moving and this is for the thermal conductivity transfer. I am assuming there is no heat generation, everything is no Bunsen burner. So this is the very much philosophical way to look at energy balance equation. Right? This is a very much philosophical way to look at energy balance equation. So what we have seen that temperature is changing with time, changing with position. Position is multi-dimensional and system has got resistance. In that case, my system is termed as parabolic system. So this equation by nature is parabolic equation because it's a time evolution problem and system has resistance. So when you have a system, you look at a chemical engineering system, you ask the question, system has resistance, yes. System is evolving with time, yes. My system is parabolic. There is no question you will think about mathematical formula. System is having resistance, system is actually evolving with time, it's a parabolic system. Now what actually happens? If there is this term not there, Okay? If this term is not there, and these terms are also negligible, okay? There is no velocity, things are not at equilibrium. Things are not changing at no fluid velocity. Initially, when you have the Bunsen-Burner switch, there is still some flow with that velocity. After some point, velocity you cannot see, everything is stagnant. So all these terms should actually go. But still, you can see the bottom wall is hot, top wall is cold. Still that is maintained. In that case, you will get simple equation, which is dou 2t dou x square, dou 2t dou y square, plus dou 2t dou z square equals to 0. This is still a partial differential equation. T is function of x, y, z. But if you see that time is missing, the steady state, I have switched off the Bunsen burner, enough time has elapsed. Okay? But still some portion is hot, some portion is cold. Because of that, because of the thermal conductivity, we have some resistance, and based on that, time is the function of x, y, z. This type of equation is an equilibrium problem, which does not evolve with time. But system has got resistance, things are varying from position to position. This type of problem is termed as elliptic problem. So elliptic means system is at equilibrium. Elliptic means system is at equilibrium, but system is having the position dependency, but it does not have time dependency. But if you have one-dimensional geometry, there is other dimensions, there is no variation. In that case, this PD will come to the ODE. In that case, the PD will come to the ODE. Okay? So elliptic PDE can be converted to ODE if the system dimension is only one. For one-dimensional case, elliptic PDE can be converted to ODE, but parabolic PDE cannot be converted to ODE. Parabolic PDE will remain as PDE. Right? So in chemical engineering found that when you can get parabolic, when you can get elliptic. When is hyperbolic? In atmosphere. Now I am putting a big box. Atmosphere. Okay? Big atmosphere or big ocean. The ocean middle of the ocean and atmosphere. What actually happens? Storm going on. Yes, storm is coming. Okay? The storm is taking the air parcel and carrying. The storm is going, it is taking the air parcel. So when the storm occurs, you feel cold, because what actually happens? Hot air from the bottom goes to the top. And why it is going to top? The top, the cold air will be coming inside because of the buoyancy. It will push away the hot air. And in that case, at particular point, temperature will change because of these terms, Vx. So in that case, my equation will be rho Cp dou T by dou T plus Vx dou T by dou x plus Vy dou T by dou y and Vz dou T by dou z equals to 0. And what actually happens? Thermal conductivity is negligible because there is no system resistance, because it is universe, there is no resistance, every point is same. If you go much far from the bottom, everything is same, because only near the bottom there is a viscous effect, there is a changing thermal conductivity. So in that case, there is no system resistance, only transport occurs because of time evolution or the convection. So basically, if you don't have any system resistance, I can tell you, that if you don't have system resistance, either you can have time dependency, or if it is steady state, you can have the convection system. In that case, system is termed as hyperbolic system. So hyperbolic system typically does not have system resistance. It could be equilibrium problem, it could be the steady state, it could be the time dependent problem. And hyperbolic equation, typical thing is, since there is no system resistance, you don't have system resistance, you get something called shock. Shock is the property of hyperbolic beam. You can try it out what the shock is. I will show you the shock, what is called shock. In everyday life, you can actually experience hyperbolic beam. is the hot wall, this is the cold wall. The temperature, cold temperature. This is the system resistance. If I reduce this and reduce this, what actually resistance will go? And so that means suddenly if I put hot and cold, you get a jump discontinuity. This is hyperbolic PD. That means what actually I can tell you that you have a hot tawa or cooking. Suddenly you touch your hand, that's it, you get burning spot. That is called shock, hyperbolic PD. Because in between there is no resistance. Hot and cold, shock. So shock is a typical criteria for the hyperbolic partial differential equation. So these are the characteristics for the partial. So basically, if any equation is given to you, you don't have to worry about, see the physics. Based on the physics, you can decide. That means if you have some term like K or some M grad square, this type of term which is known as resistive term. If you have B bar dot del grad T, this kind of term, this is the advection term. So when you have the grad square term, for example, immediately you can say my system cannot be hyperbolic, either elliptic or parabolic. Okay? In that case, you see, but the time dependence is there. If time dependence is there, okay, your system is parabolic. The time dependence is not there, system is elliptic. Okay, so we have done quite a bit of the fundamentals of the partial differential equation. So let's look at what are the kind of boundary conditions we have. I'll just take another 4 minutes. Did I discuss boundary condition? Dirichlet, Neumann and Robin's boundary condition earlier? In the first class, very first class, we have the class course. Very first class. Dirichlet, Neumann and Robin's boundary condition. Did I discuss? Yes or no? No. Okay. I will discuss once again. Even if you could not find, no problem. I will discuss and leave the class. So when I say a cavity and I say hot wall and cold wall, that means I maintain the temperature here. Whatever happens here, I maintain the hot, I maintain the cold here. How to maintain? Sometimes what actually happens, we can actually pass saturated steam here. Saturated steam is always maintaining the same temperature. Whatever happens, you don't change the temperature. Here you can actually pass the cold, ice cold, pass the ice cold water, or the phase change material, PCA material. Maintain temperature. So whatever actually happens, your temperature will not change, or in the velocity, for example, the pipe flow, no slip boundary condition. Whatever happens, no slip is still valid. So these kind of conditions are called as Dirichlet condition, that the functions will not change. Whatever happens in the domain, whatever happens in the domain, function will not change. Whatever happens, the domain function will not change. Next is, I will talk Robin's condition, then go to Neumann. Solid and fluid. Okay? The heat is coming by conduction here. Solid. Lost by convection. Fluid. How the typical equation here at this domain? Any idea? Anybody can tell? What is the typical equation? Balance equation. Heat is coming by conduction, going here by convection. What is the typical equation? What is that? What is that? Arbitrarily you are doing something, I know that. What's the heat flux by conduction? You know heat flux part. Minus K dou T by dou S equals to, what's the heat loss by convection? How to write? If the fluid temperature is infinity, balance. This is called as Robin's condition. Okay? I will just expand minus k dou t dou x plus ht equals to ht infinity. We look at derivative and function, both are actually happening. The boundary condition. This type of boundary condition is called as mixed boundary condition or Robin's boundary condition. Mixture of function and the derivative. If this partial part is insulated, what actually happens? Dou t dou x equals to 0. No heat loss. Minus k dou t dou x equals to 0, and that will give dou t dou x equals to 0, which is called as homogeneous Neumann boundary condition. Which is called as homogeneous Neumann boundary condition. If it is insulated. So from Robin's boundary condition, one can get Neumann and Dirichlet condition, which is minus k dou t dou x equals to h t minus t infinity dou t dou x equals to h by k t minus t infinity. What actually happens if k tends to 0? If k tends to 0, you can just put it here k tends to 0, which is t minus t infinity equal to 0, which is t equal to t infinity. So if k tends to 0, Robin's condition will go to the Dirichlet condition. If k tends to infinity, what actually happens? This will become the homogeneous Neumann boundary condition. So next class will meet on Monday.